let's do this starter problem. And here's what's given. You've got a 12 kilogram mass here on wheels, and we've got this force on it that's going to accelerate it to the right. It starts off with 2 meters per second, but the force is not constant with time. So you can't use the kinematic equations, but we can use impulse and momentum and the impulse momentum theorem. We want to know what was the impulse on here, what is the change in momentum. Should put a vector hat on there. What's the change in velocity, or what's the final velocity if the initial velocity is 2 meters per second? So here's the, but here's the deal. Here's what's also given. The force is a function of time. And so it starts off with 4 newtons for 3 seconds, and then for the next 2 seconds, it decreases to 0. So let's solve for A. We want the impulse. Now, where is the impulse in this graph, as we talked about last time? Well, it's the area underneath the graph. So the impulse equals the area of a force versus time graph. Okay. So we'll say I equals the area. Well, I've got a rectangle, so I'll just go base times height plus a triangle, 1/2 the base of that triangle times the height. So the base of this is 3 seconds, and the height is 4 newtons, plus 1/2, well, the base of the triangle is 2 seconds, and the height is 4 newtons. Okay, so we get 12 Newton seconds plus 4 Newton seconds, for a total of 16. So the impulse is equal to 16 Newton seconds to the right, and the force is to the right, so we'll say that's to the right. So that's the impulse. Make sense to everybody? Well, for part B, and let me zoom out a little bit here. For part B, now we can apply the impulse momentum theorem, where it says the force times time, which is the impulse, is equal to the change in momentum of the object. So now we know what the change in momentum is. It's 16, but instead of using Newton seconds, momentum is measured in kilograms times meters per second, mass times velocity. And that's all you need to know for part B. If you know the impulse, you know the change in momentum. They are equal. And I just changed the units a little bit. And if you get that mixed up, I'm not going to mark things wrong if you have Newton seconds instead of kilogram meters per second for change in momentum. Now part C, now we know what the change in momentum is. Well, that's equal to the final momentum minus the initial momentum. Well, that's equal to the mass, and the mass stays constant. So that's going to be final velocity minus the mass times the initial velocity. So, and this is going to be equal to 16 kilogram meters per second. So now I can solve for this. So I'm going to add this to the other side and then divide by the mass. So the final velocity will be equal to 16 kilogram meters per second minus, or I'm sorry, plus, because we're going to add this to the other side, plus the mass. I'll go ahead and plug in numbers here. 12 kilograms times the initial velocity was 2 meters per second. And then we have to solve for the final, we have to divide by the mass. 12 kilograms. And so, and this will be equal, am I still on screen? Oh. So this is going to be equal to, well, let's see, 12 times 2 is 24. 24 plus 16 is 40, is that right? Yeah. And then 40 divided by 12. And so our final velocity is going to be 3.3 meters per second. Yeah. Any questions? I got to answer the phone. So that is all. Mr. Lake. Yeah, hold on. Cameron Biggs, it's for you. Oh, I'm still recording. That's all.